The first class on Legendre differential equation, we stated that the Legendre differential equation arises when one solves Laplace's equation in spherical polar coordinate system. Then theta equation leads to associated Legendre differential equation. And for spherically symmetric situation, azimuthally symmetric situation, and for phi independent case, one encounters Legendre differential equation. The Legendre differential equation is 1 minus x square y double prime minus twice x y prime plus alpha y is equal to 0, where alpha is any real constant. X is equal to 0 being a regular point, we applied power series method. We applied power series method for its solution, and we assume that y of x is equal to summation over k is equal to 0 to infinity ck x to the power k with c0 not equal to 0. Then we lead to the recurrence relation like this: Cn plus 2 is equal to n into n plus 1 minus alpha n plus 1 n plus 2 Cn. So for in general values of alpha, the solutions are infinite series solution. One series starts with C0 and comprises of C0 C2 like this. Even series is C0 C2 x square C4 x to the power 4, which we designated as even series. And other series starts with odd one, C1x, C3x cube, C5x to the power 5, and so this is the odd series or odd solution. We see that for general value of alpha, both the solutions are infinite series solution, so we need to check their convergences. It was further found that if we apply ratio test, the series is found to be convergent for mod x less than 1. But the Legendre differential equation is applied in the closed interval between plus minus 1, that is, it is generally applied in this interval. X is equal to plus 1 corresponds to positive z axis, x is equal to minus 1 corresponds to negative z axis. So the use of powerful test, that is the Gauss test, which is a second order test and is obtained from the Riemann zeta function and is obtained by a comparison with the convergence of Riemann zeta function. It is found that the infinite series solution diverges at x is equal to plus minus 1. But in most of the physical system, the z-axis is included within the system, and we have if we want to have a finite solution, then we must find a way out of this, that is, the solution will become still infinite series. The solution will be a finite one even on z-axis. To that end, we have seen that alpha cannot take any real value, but alpha has to take few non-negative integral values given by this. So the values are 0, 2, 6, 12, and so on and so forth. And if we use alpha in this case, in this fashion, then the recurrence relation, as we have done in the earlier class, becomes Cn plus 2 is equal to minus L minus n, L plus n plus 1, Cn. Then with this we go to the even series, and for even series we obtain that the general term C of 2k is equal to minus 1 to the power k 2k factorial 2k factorial times C0. This is the general expression. We see that for even values of L, say L is if L is equal to 2, say, then C0, C2 are non-zero and C4 onwards are 0. So we have C0 and C2, they are not equal to 0, C4, C6 onwards are 0. So for even value of L, this even series becomes a polynomial of order L having L by 2 plus 1 number of terms. We have explained this in the earlier class. For odd values of L, this solution is in the form of infinite series. So our conclusion, the conclusion of the previous class is that if L is an even quantity, even integer, then the even series becomes a polynomial, but for odd values of L, the y even remains an infinite series. Now we come to the odd series. Odd series starts with C1, and for this we write Cn plus 2 is equal to minus L minus n, L plus n plus 1, n plus 1, n plus 2 Cn. For n is equal to 1, we get C3. So what we get for n is equal to 1, C3 is equal to minus L minus 1. This is n is equal to 1, so L plus 2. And here we have 2 into 3 C1. For n is equal to 3, n is equal to 3, we have C5. So in this case, this is minus L minus 3, and this much is L plus 4. 4 into 5 C3, this is equal to plus L minus 1, L minus 3, L plus 2, L plus 4, factorial 5 C1. Obviously C7, the expression for C7 is minus L minus 1, L minus 3, L minus 5, and then this part L plus 2, L plus 4, L plus 6, factorial 7 C1. So we can generalize the term. In this way, C of 2k plus 1 is equal to minus 1 to the power k You see, this factor is for 3 it is 1, for 5 is 3, for 7 it is 5. So, it is L minus 2k plus 2, and then we have L plus 2, L plus 4, and you see that this is 2, 4, 4 for 5, 7. So, this is L plus 2k minus 1, C1 2k plus 1 factorial. So, this is the expression for all series. There were two mistakes. One, this should be 1, and this is simply 2k. Now, please note these two corrections. Because for 7 it is 5, so this is L minus 2k plus 1, then minus 2. Sorry. This is simply this one. So, this is L minus 2k plus 1, this is the right, and this term is simply 2k. Now, you see that the if L is equal to 1, if L is equal to 1, C1 is not equal to 0, C3 is equal to 0, then the series is simply C1x, and number of terms is 1. For L is equal to 3, C1, C3 are not equal to 0, C5 onwards are 0, and the series is, the number of term is 2. Then in this way fashion, if L is equal to 5, if L is equal to 5, then C1, C3, C5, they are not equal to 0, C7 onwards are 0, so the series is y odd is C1x, C3x cube, C5x to the power 5. Now, if we come to the number of terms is 1, number of terms 1, 2 and 3. These are the capital N values. Now, if we want to relate this is simply L plus 1 by 2. When L is equal to 1, this is 1, L is equal to 3, 2, L is equal to 5, it is 3. So, this is an, so we see that if L is odd, L is an odd integer, the odd series is a polynomial of order L, and the number of terms is given by this. But for even values of L, this remains as an infinite series. So, our conclusion is that for any real alpha, both the solutions are infinite series with divergence, having divergence at x is equal to plus minus 1. This is 1. If alpha is equal to L into L plus 1, where L is non-negative integer, where L is integer, then two cases arise. One is if L is even, then y even is a polynomial. Polynomial of order n, and y odd is infinite series. If L is odd, then y even is infinite series, and y odd is a polynomial. That is, for general value of alpha, say alpha is equal to 1.5, both the solution are infinite series which diverges at the on z axis. If we choose some special values of alpha, so we say that alpha values are quantized. If the alpha values are quantized in this fashion, then two cases may arise. L is even, then one of the solution, that is y even, is a polynomial, but this is a divergent one, y odd. If L is odd, the role is reversed. So if we choose alpha in this fashion, then one of the solution is polynomial, which is finite even at x is equal to plus minus 1, as it comprises of even finite number of finite terms, and another solution is an infinite solution. The nomenclature is this, like this. The polynomial solution is known as the polynomial solution, which is generally denoted as PL of x, is known as Legendre polynomial or Legendre function of first kind. The infinite series solution which is denoted as QL of x is known as Legendre function of second kind. This is not a polynomial. Note that a PL at x is equal to plus minus 1 are finite. QL at x is equal to plus minus 1 divergent. But QL is finite between x is equal to plus minus 1. Now, with this knowledge, we now go to an expression for the Legendre polynomial. Now, in this we shall use the recurrence relation to derive an expression for the polynomial series for a polynomial or the Legendre function of first kind. To this end, what we do, we first rewrite this expression. This recurrence relation was this is the recurrence relation with alpha is equal to L into L plus 1. We rewrite this expression in terms of C. So, this Cn is equal to minus n plus 1 n plus 2 this is the expression. So, we first rewrite this as we put L is equal to n is equal to L minus 2 for what we will have, we have C of L minus 2 is equal to minus. This is L into L minus 1, the numerator factor, it is 2, then this is 2L minus 1 CL. For n is equal to L minus 4, we have C of L minus 4 is equal to minus this term will be L minus 2, this is L minus 3. This term will be 4 and this term will be 2L minus 3 C of L minus 2. If we use the expression of CL minus 2, this becomes plus L into L minus 1, L minus 2, L minus 4, and then we have in the numerator 2, 4, 2L minus 1, 2L minus 3, CL. For n is equal to L minus 6, we have C of L minus 6 is equal to minus. This is n minus 4, this is n minus 5. L minus 4, L minus 5. The denominator term, this one is 6 and the other one is 12 minus 5. Which can be generalized easily. So, we generalized it as C of L minus 2k because the decrease by 2. So, this is minus 1 to the power k. In the numerator, we will have L minus 1, this is L minus 2, for minus 2 it is 1, for minus 4 it is 3, So this is 2k plus 1. So in this case k is equal to 1, k is equal to 1, so it is L minus 1. In this case it is k is equal to 2, so it is L minus 3. The last term is L minus 3. Yes, there is a wrong. It should be 3. And for this, k is 3, so it is 6 plus 1, so it is minus 5. And the denominator we will have 2, 4, 6 up to 2k. This is one sequence arising from this part, and there is another sequence 2l minus 1, 2l minus 3, and this continues up to 2l minus 2k plus 1 CL. This is the recurrence relation. Let me check. We write it as minus 1 to the power k. This is the numerator term. There are two terms in the denominator times CL. Now let me first simplify. N is the numerator, so it is L into L minus 1, L minus 2 up to L minus 2k plus 1. This term is written like this. Then the next term L minus 2k. So you multiply L minus 2k in the numerator, we divide this. Then the term is L minus 2k minus 1. So L minus 2k minus 1 up to 3 to 1. The numerator part is L factorial, and denominator part is L minus 2k factorial. D1 is 2, 4, 6 up to 2k. So this is, if we take 2 common, there are k terms, so it is 2 to the power k, then 1, 2, 3 up to k. So it is 2 to the power k times factorial k. Now come to the last term. This is D1. This is D2. So we rewrite this term as, first we write a term 2l over here, which were not there. So to adjust, we write 2l. Then 2l minus 1 was there, 2l minus 1 was there. Then we write 2l minus 2, which is not there, so we adjust it, 2l minus 2. In this way, we go on multiplying a term in the numerator and adjust it by multiplying the same term in the denominator. The just previous term was 2l minus 2k plus 2, which were not there, so we write 2l minus 2k plus 2, and the last term is this term was there. This is the adjustment. Now, you see that the denominator part, what can you write? If you take 2 common, there are k terms. So, this is 2 to the power k. Once you take k common, this is L minus 1. So, this is L minus 1 through L minus k plus 1, and this is this term is 12 minus 1 up to this. The numerator of it can be written as 2l factorial divided by 12 minus 2k factorial. We have multiplied this by 12 minus 2k up to 321, and it has been adjusted. And this part is written as 2 to the power k. This can be written as L factorial by L minus k factorial. So, altogether this term becomes 2L factorial. This will go in the numerator, L minus k factorial. Then we have 2 to the power k L factorial and 12 minus 2k factorial. That's all. Let me check, it's a complicated calculation. L minus k to the power. We use all this result over here. So, we get for minus 1 to the power k. For numerator we write this one, L factorial by L minus 2k factorial. This is for the numerator n. This is for n. Then d1 divided by d1. So, d1 is 1 upon 2 to the power k factorial. This is for, this is for d1, and for d2 this part will come in the denominator and this part will go to the numerator. So, this is 2 to the power k L factorial 2L minus 2k factorial CL. This part is for 1 by d2. So, the term that cancels out, this cancels out. This is L modulus, L factorial square. Let me. 2 to the power k gets cancelled. So, in the numerator we will have L factorial square times 2L minus 2k factorial. In the denominator we will have this one L factorial, then k factorial, L minus k factorial, L minus 2k factorial CL. CL is chosen as, one chooses CL as 1 upon 2 to the power L factorial square. So when we write this L factorial square cancels out. One chooses CL like this, and when we use CL in such a fashion, then this expression, you see that L factorial square cancels out, 2L factorial cancel out, we get, in the numerator we will have 12 minus 2k factorial, in the denominator we will have 2 to the power L k factorial, L minus k factorial, L minus 2k factorial. And so with this choice, the polynomial solution becomes PL of x zero to capital N. I am defining capital N. So this is the expression for Legendre polynomial as a descending series. If we write C12, this becomes minus 1 to the power k, then we use the expression this is the final expression for, so this is 12 minus 2k factorial, in the denominator we have 2 to the power L k factorial, L minus k now the k value, the minimum value of k is 0 indeed. What will be the maximum value of L? That is determined by the property of the factorial. For integral values, it is found that the factorial of negative integer is not defined, it blows up. Only factorial of 0 is defined by convention. Factorial of 0 is 1, and so as k go on increasing, if k increases beyond this value so that the quantity becomes negative, it will be cut off. So the k max value is such that L minus 2km is greater than or equal to 0, which such that km is less than equal to L by 2. It is found that for integral even value of L, even value of L, we define, for even value of L, we define a quantity like this. So the range is this. Let me work out few simple low order Legendre polynomial using this series. So PL, as per this expansion, PL is equal to summation over k is equal to 0 to n minus 1 to the power k 12 minus 2k factorial to the power L k factorial L minus k factorial L minus 2k factorial x to the power L minus 2k. Now first L is equal to 0, so we get P0 of x. So L is equal to 0, you have 2 to the power 0 is 0, then we write it as summation over k minus 1 to the power k. This is 1, 2 to the power 0 is 1, so it is k factorial minus k factorial minus 2k factorial and minus 2k factorial. So we see that only k is equal to 0 value is allowed, and we have x to the power minus 2k. Only k is equal to 0 is allowed, only k is equal to 0 is allowed, in which case this is simply 1. Check it. For L is equal to 1, we have P1 of x. Let me write this expression summation over k. Then minus 1 to the power k. In the denominator we will have 2 to the power L, that is 2 to the power 1 k factorial 1 minus k factorial 1 minus 2k factorial 2 minus 2k factorial x to the power 1 minus 2k. If k is equal to 0, it's no problem, and if we put k is equal to 1, this term becomes negative. So only k is equal to 0 is allowed. And which case k is equal to 0, if we put it, then the sign goes, this is 2 factorial in the numerator, 2 factorial, 2, 0 factorial, 1 factorial, this is 0 factorial, 1 factorial, again 1 factorial into x. So this is x. Now come to the L is equal to 2. For L is equal to 2, we have P2. This is 4 minus 2k factorial. In the numerator we have 2 square k factorial, 2 minus k factorial, 2 minus 2k factorial, x to the power 2 minus 2k. Now if we put k is equal to 0, no problem, and if we put k is equal to 1, this becomes 0, and you cannot have other values. So only k is equal to 0 and 1 are allowed. So we have, for k is equal to 0, the numerator this sign is positive, this is 2 to the power 2, that is 4, this is 0 factorial, this is 2 factorial, and this is again 2 factorial, times x to the power we have square, Then for k is equal to 1, this term is negative, the sign is negative, and this is 2 factorial in the numerator. So k is equal to 1, 2 factorial, this 4 is from here, then 1 factorial, then 1 factorial, then this is 1 factorial, and this is 0 factorial, and x to the power 0. Factorial 4 is 4, 3, 2, 1 is 12. So when this is in the numerator, we have 12, then 4 into 4, so 16. So this is 3 by 4. Definitely missed some factor. There was a blunder. It should be 24. So the factor is 24 by 16. So it is 3 by 2, simple. So the factor is 3 by 2 x square minus half. So taken half common, this is 3 x square minus 1. In this fashion, you can go for higher orders, and as homework, I give you calculate P3, P4 and P5 using this expansion. In the next class, we shall discuss the Rodrigues formula in connection with Legendre differential equation.